As aging progresses, the capacity for physical activity often declines, either due to musculoskeletal limitations, cardiovascular compromise, or chronic conditions that reduce endurance and mobility. This poses a serious challenge for maintaining healthy body composition in the elderly, since exercise is one of the most effective interventions for promoting autophagy, reducing visceral fat, and improving metabolic flexibility. In this context, the emergence of NMN, nicotinamide mononucleotide, as a compound capable of mimicking certain biochemical effects of exercise, particularly in the activation of autophagy, presents a compelling opportunity to help aging individuals manage weight and preserve metabolic health even when regular physical activity is not feasible. Exercise induces autophagy primarily by creating a state of transient energy deficit. This activates AMPK and suppresses mTOR, thereby stimulating autophagosome formation and initiating the degradation of damaged cellular components, including dysfunctional mitochondria. Concurrently, exercise elevates NAD levels, which further activate sirtuins, especially SIRT1 and SIRT3, supporting mitochondrial biogenesis, lipid oxidation, and autophagy-related gene expression. NMN supplementation acts along these same pathways by replenishing NAD, thereby triggering downstream metabolic effects that resemble those observed during moderate endurance exercise. In preclinical models, aged mice treated with NMN show increases in EMPK activation, enhanced SIRT1 signaling, and a rise in LC3-2 and Beclin-1 expression, molecular markers of autophagy that mirror those induced by treadmill or voluntary wheel running. Notably, these changes are accompanied by reductions in adiposity, improved insulin sensitivity, and enhanced mitochondrial respiration in skeletal muscle and adipose tissue. This suggests that NMN can recreate the cellular stress signals that normally arise from physical activity without the need for muscular exertion. For older adults who cannot exercise adequately due to frailty or illness, such mimetic effects are not merely beneficial, they may be essential. The fat-reducing effects of NMN-induced autophagy stem from its role in remodeling dysfunctional adipose tissue. With age, white adipose tissue becomes inflamed, hypoxic, and metabolically inert, characterized by enlarged adipocytes and a suppressed capacity for lipolysis. Exercise usually reverses this by enhancing autophagic clearance of damaged mitochondria, mitophagy, and reducing inflammatory signaling. NMN appears to replicate this remodeling. Animal studies show that NMN reduces P62 accumulation and promotes mitophagy in adipose depots, thereby rejuvenating the metabolic function of fat cells. This leads to smaller, more insulin-sensitive adipocytes and a shift toward higher fatty acid oxidation, outcomes strongly associated with reduced fat mass in aged subjects. Beyond white fat, NMN may also stimulate the browning of adipose tissue through an autophagy-dependent mechanism. This browning process increases the number of mitochondria within white adipocytes, making them behave more like energy-burning brown fat cells. Since physical activity is one of the strongest stimuli for this thermogenic conversion, NMN's ability to induce similar mitochondrial biogenesis and mitophagy suggests that it may serve as a partial substitute for exercise in this context. Increased UCP1 expression and mitochondrial density in subcutaneous fat depots have been observed in NMN-treated older rodents, particularly when autophagy pathways are intact, indicating that NMN helps restore the fat-burning machinery that usually declines with age and sedentary behavior. On a systemic level, NMN also improves energy expenditure and glucose handling, two key hallmarks of physical fitness. In elderly mice, NMN supplementation leads to increased oxygen consumption, higher basal metabolic rates, and better glucose tolerance, mirroring changes seen in exercised animals. These outcomes are likely due to a combination of enhanced autophagy, mitochondrial function, and reduced inflammatory burden in metabolically active tissues like the liver, muscle, and adipose tissue. Notably, these benefits persist even in the absence of forced activity, reinforcing NMN's potential as a therapeutic option for those unable to exercise. While the biochemical mimicry of NMN is not a complete substitute for the mechanical, cardiovascular, and neurocognitive benefits of real physical activity, its ability to reproduce the intracellular effects of exercise, especially the activation of autophagy and fat turnover, makes it an important tool for metabolic care in older populations. Early human studies show that NMN is well tolerated, raises NAD levels, and may improve markers of muscle insulin sensitivity and physical endurance over time, though larger and longer trials are still needed. For elderly individuals who are immobile, disabled, or recovering from illness, NMN offers a promising bridge, helping maintain some of the cellular housekeeping and metabolic resilience normally afforded by exercise. By restoring autophagic function in fat and muscle tissue, NMN contributes to healthier aging trajectories, with better weight control, reduced visceral fat burden, and enhanced energy homeostasis. As our understanding of autophagy deepens, so too does the promise of exercise mimetics like NMN in redefining how we approach aging, especially in populations where traditional lifestyle interventions are no longer accessible.